I had a request. You're having a little bit of trouble with some of your homework on 12. So I wanted to go over a few of the problems that might help you. Let me pull up the app right here so I can draw. And again, if you ever have any questions about the homework, and we could either do a live session or I could do like I'm doing now and just do a vodcast. I guess what's nice about the vodcast is that um, you can slow it down and pause it and really think about it. So there's, some advantages. Again, it's not live, but um, again, pros and cons. So the first one was number 7. Now, number 7 deals with 12 when we did solutions. There's a lecture in there that went over parts per million and molarity and molality, all of that. It's in that section. So what this says, it says, and your numbers might be a little bit different, express the concentration, 0.07 molar aqueous solution of fluoride in mass percent and in parts per million. Assume the solution is 1 grams per million. Okay, so let me set this up for you. We have a solution. The molarity is 0.07. Now, before we can begin this, we need to define molarity. Molarity is moles of solute over liters of solution. We know this is of fluoride, and we know the liters of solution since it gave us a density equals 1. We can assume it's water because the density of water is 1. Anyway, so let's see what we have here. And let's also look at what we're trying to find. We're trying to find the percent mass, okay? Percent mass equals to mass of solute over mass of the solution. And since it's a percent, we multiply this by 100. Now the parts per million, the only difference here is the same formula. I'll just put little quotes here, except instead of multiplying by 100, you're going to multiply, remind me later, sorry about that. You're going to multiply by 1,000,000. Oops, not a 1. There we go. Okay, so let's set this up. We have moles. Okay, so this is 0.07 and then over 1 liter. Okay, that's another way of writing it. Moles, this is our moles of solute, and this is our liters of solution. So anytime they just give you a number like 0.07 molarity, the top number is always your moles, and it's always over 1 liter. Okay, so the first thing we need to do, change my color, is we need to get, where's our formula? Right here. Mass, which is in grams, of solute. Right now, I have it in moles. So let's convert that. So I have 0.07 moles of fluoride. Now to convert that to grams, I just do 1 mole of fluoride. And then I look at the molecular weight on the periodic table, which is about 19 grams of fluoride. My moles will cancel out, leaving me with 0.07 times 19, which is 1.33 grams. Okay, so now I have grams of solute. Great. Now let's find the grams of the solution. I have 1 liter here, and I can convert it using this right here, the density. I know the density is 1 gram per milliliter. So I have 1 liter. Now notice this is in milliliters, so I need to convert this here to milliliters first. So 1 liter equals to 1,000 milliliters. And now I can put the density in. 1 milliliter is 1 gram. Cancel out the liters, cancel out milliliters, leaving us with grams. So when I do 1,000 times 1 divided by 1, I get 1,000 grams. Now again, the reason I had to convert it to milliliters first is because this unit conversion had milliliters and not a liter in it. Okay, now I have the mass of the solution. So let's put this in the formula. I have 1.33 divided by 1,000. I'm going to multiply this by 100. Okay, now when I do that, I get 0.133, and that is my mass percent. Now, I'm not going to fully do it for you so you can work it out, is if you're doing the parts per million, then you use the same formula. So you're going to, this part right here will be the same, except now instead of multiplying it by 100, you'll multiply it by a million, and that'll give you your number there. So I hope that helps with that type of problem. Now I'm going to pause it for a second so I can set up the next one for us. Okay, so here's the next one. It's number 10 on the homework. And it says at 25 degrees Celsius and 765 torr, carbon dioxide has a solubility of 0.0342 molar in water. What is the solubility at 25 degrees Celsius and 1770 torr? Okay, anytime in chapter 12 they talk about solubility and pressure. Okay, so let me write this down. Oops, that's not this app. Okay, if they talk about solubility and pressure, if those two words are mentioned, this is a Henry's Law problem. It's important to know what formulas you use for each question. So Henry's Law says solubility equals to K times P. Solubility, S, P for pressure, so that's why you have solubility of pressure. K is a constant for each substance. So does it make sense that if I use carbon dioxide versus carbon monoxide, the solubility will change just because it's a different chemical, okay? So this will be a constant. Either they'll give you the constant or they'll link you to a chart to look it up yourself, okay? So this here, again, is a constant that somehow will be given to you if you need it. So let's look up what we have. So our first solubility, or actually we'll say our first pressure 1, was given to us in the problem as 765 torr. And our solubility for the first one was 0.0342 molar. Okay, now for the second part, it said, okay, so originally you had 765 torr and your solubility is 0.342. Sorry. Now let's say the pressure, let's increase the pressure to 1,770 torr. Now, what is the solubility? What does that do to it? Okay, now let's just look at this. And so if you see here, these are directly related, meaning if you increase S, you'll increase P, or if you increase P, you increase S. Okay, so they're directly related. If it was like this, S equals to K over P, so now this one's at the bottom and this one's at the top, then they're indirectly related. I just want to show you how you could figure that out pretty easily. So let's look at this formula here. S equals to Kp. Now in both of these, we're using carbon dioxide, both substances. And so we're not changing what we're using. So the K for both of them is the same. So I could set this up. Let's solve for K. S over P equals to K. Okay, and this is for number 1. Number 1, I'm meaning, these set of numbers. And then for number 2, S equals to Kp. So if I solve for S, S over P equals to K. Now remember, the K's for both of them are the same because it's the same substance. We're still looking at CO2. So because of this, I could set them equal to each other. Now let me call this S1, P1, S2, P2. So when I do that, I could say S1, P1 equals to S2, P2. Again, that's because the K for both of these will be the same because I'm still looking at CO2. So I can set these equal to each other, because if this divided by this equals to K and this divided by this equals to K, then I could set S1, P1, S2, P2 equal to each other. So let's put in our numbers. S1 is 0.0342. P1 is 765, getting the numbers up here, equals to S2, we don't know S2, we're trying to find that, S2. And then P2 is 1,770. Okay, so now we just cross multiply. And when you do this, make sure you know how to do this. If you don't, contact me. And you just do this, divide by this, multiply this, and then divide by this. But you have to do it step 1, this, multiply this, then divide by that. And I'll give you S2. But when you do it, you should get S2 equals to 0.079 molar. And actually, you're going to put 2 in there because you need 3 significant figures because all of these numbers use 3. Okay, and that is your final answer there. Okay, so I hope that helped with this problem. Now let me stop here and look at the next one. Okay, let me do this one for you. I'm going to do part A, and then I'll kind of really quickly show you part B. So this one here is another Henry's Law. Well, it says Henry's Law, and plus they talk about solubility and pressure, okay? So it says at 298 K, and notice that all the temperatures are at 298, so the temperature doesn't matter. Henry's Law constant, which is the K, is 0.0013 molarity per atmosphere. Air is 21% oxygen. At 298 K, what is the solubility of oxygen in water exposed to air at 1 atmosphere? Notice it's exposed to air. It doesn't say the pressure of oxygen is 1, it says the pressure of air. And air is only oxygen is only 21% air. So let me show you what to do with that. Because otherwise it'd be a pretty simple problem. You have an S, you have a K, you have a P. The little trick is just that 21%. What do you do with that? Okay, so first off, we have our formula. Solubility equals to Kp. And let's see, I wrote down the numbers here. The the K they gave us is 0.0013 molarity per atmosphere. We know that 21% of air, the pressure, or oxygen. Oxygen is 21% of the pressure. We know the total pressure of air is 1. Okay, so the total pressure is 1, but air is only 21% of that, so you have to do 1 times 0.21. Why 0.21? Because it's a percent. A percent is always the number over 100, which equals to 0.21. So if I do 1 times 0.21, then the actual pressure is 0.21 atmosphere. So we have, we're trying to find solubility. Solubility equals to K, which is 0.0013, times the pressure, which is 0.21. So the solubility equals to 0.00273. Now for the next one, the only difference is that instead of using 1 atmosphere as the total, it was, I think, 0.873 or something like that as the total pressure of air. So then you just do the 0.21 times that number to get your new pressure. So instead of using 1, you have a different number to get you your pressure. And then everything else, you just plug in the numbers. Okay, so that's 2 different problems over Henry's Law. Hopefully that gets you an understanding of that. Now let's go on to another one, Raoult's Law. This one has to do with vapor pressure. So anytime they're talking about vapor pressure, and they start throwing in moles or molarity or something, then this is Raoult's rule. So let's This one is, let's see, vapor pressure of a solution. It's important that this part, all these parts, um, you understand the mole fraction of the solvent and the pressure of the solvent. Okay? So what happens is, let me explain this a little bit. In my little beaker here, I have a solvent. Let's just say it's water. I can't spell H2O. Okay, and let's say I put in some salt in here. Okay, so before I had salt, this was 100% water. So my mole fraction is 1. Okay, but now I put in some salt, Here's my little salt granules. Now it's not 100% water. Let's say now it's just 98% water. So I'm going to put 0.98, and I have a pressure of the solvent. I don't know the pressure of this. Let's just say it's 5. Okay. Before, when I just had water, it was 100%. So I just say 1 times 5. So the solvent pressure would be 5, and then to define the solution, it would just be 5 because it's the same because I didn't add anything to it. Now, when I added the salt in there, now it's only 98%. So now it'd be 0.98 times 5, so maybe it's now, I'm not going to, 4.96, okay? So now the vapor pressure of the solution has decreased, okay? Vapor pressure is an indicator of how easily something can be dissolved, if you want, okay? Not dissolved, I mean, like boil. You're looking at boiling point, and you're looking at intermolecular forces and everything, okay? So the lower the vapor pressure, the harder it is to boil it. Okay, so let's look at this. We're looking at changing the vapor pressure. Now let's look what our actual problem says. I'm looking at number 12. Biphenyl C12H10 is a non-volatile, non-ionizing solute that is soluble in benzene. Okay, so I have biphenyl, which is C12H10, and I wanted to dissolve it in benzene, C6H6. At 25 degrees Celsius, the vapor pressure of pure benzene is 100.84 torr. So this is the pressure of the solvent. So before I add anything to it, it's 100.84. Now I want to know what is the vapor pressure of the solution after I've dissolved 12.7 grams of biphenyl and 25.5 grams of benzene. So initially I had 25.5 grams of benzene and the vapor pressure was 100.84. But I'm putting in 12.7 grams of biphenyl. Now what is the new vapor pressure? So let's do that. So here is our formula right here. And let me change my color. Okay, let's put down my numbers. Vapor pressure of a benzene, pure benzene before I've added anything, is 100.84. And I have 25.5 grams of benzene in my beaker. But now I'm going to add 12.7 grams of biphenyl. What is the new vapor pressure of the solution? Solution meaning of the combination of these two. What is the new vapor pressure? Okay, so the first part, which is I guess the hardest part, I need to find the mole fraction of the solvent. Notice it's the solvent, not the solute. So mole fraction is going to be moles of solvent over moles total. So I have grams of both of these. I need to convert these into moles. So I have 25.5 grams of benzene. And that's C6H6. So if I add that up, I get the molecular weight of benzene. I have 6 carbons, 6 hydrogens. The molecular weight is 78 0.1 grams per 1 mole. So if I divide these two by each other, I get 0.326. And remember, this is a benzene, so this is of my solvent. This is my initial, because that's what I had in there initially. And then what I add in there is my solute. So biphenyl, I add everything up, I get the molecular weight, and that is 154.2 grams per 1 mole. I divide those so I can get the moles, and that is 0.082 moles. Now, to get the mole fraction here, let me change my color again. Moles of solvent, which is 0.08, no, solvent, sorry, that was my solute. My solvent was 0.326 mole, and then my total of everything combined is 0.082 plus 0.326. Remember that. It's not going to be solvent over solute, it's solvent over total. So add all of them together. So when I divide this all out, I'm going to get 0.79. Okay, so that's just my mole fraction. But now I have everything I need. I have my mole fraction and I have my vapor pressure of my solvent. So I just multiply those. So vapor pressure of benzene is going to be my mole fraction of the solvent, which is 0.79, times right here, vapor pressure of pure benzene, which is 100.84. And so then my vapor pressure is 80.5. So now if you see 0.79, that means that only 79% of my solution is benzene. It used to be 100, but now it's 0.79. So my vapor pressure went down to 80.5 by adding that biphenyl to it. Okay, so that's a Rauolt's example. Let me do one more. Okay, let's look at number 13. This is a freezing point, depression, boiling point, elevation. This has to do with vapor pressure too, but for example, why do we put salt on the road whenever it's cold outside? You know, we were looking at freezing point. Well, because in this case, it lowers the freezing point. We're looking at freezing point depression. So water freezes at 0 degrees Celsius, okay, or 32 Fahrenheit, okay? But if we lower the freezing point by putting some sort of salt on it, think about it, we're lowering it, so the temperature has to get lower for it to freeze, so it just makes it harder to freeze, and that's why we do it, okay? So the temperature has to get lower. Now, how do we solve that? Okay, well, you're going to use specific formulas for freezing point and boiling point. Now, I'm just going to do freezing point because boiling point's exactly the same calculation almost. Okay. So the freezing point, so it's the change in freezing point we're actually going to solve for. That is the constant times the molality of the solution. Molality. Okay? Now molality is different from molarity, is moles of solute over kilograms of solvent. Molarity is moles of solute over liters of solution, so it's different. Now, they gave us the moles of the solute in the problem. That was 0.593. And they said the grams of solvent equals to 763. Remember, this is a grams, okay? But, okay, moles of solute, great, but we need kilograms of solvent, okay? So I have 763 grams there are 1,000 grams in 1 kilogram. So if I divide that out, I'll get 0.763 kilograms. Now I can put this into my formula. Molarity is 0.593 over my kilograms that I found there, which is 0.763. This number is 0.777 molality. Now, there's a chart they gave you. If you click, let me show you, right here, and we're looking up for benzene. There it is. Here it is, benzene, okay? Now, the Kf, we're looking at freezing point, so Kf is your freezing point constant, Kb would be boiling point. This is 5.12. And also notice that your freezing point is 5.49. So the temperature is 5.49 and the constant is 5.12. So I know that my constant right here for benzene for freezing point is 5.12. So in my formula, I have 5.12. So change in freezing point is 5.12 times the molality, which is 0.777. I just calculated, and that will give me 3.98 degrees Celsius. Now, I'm not quite done yet. This is just the change in temperature. That means adding this compound to the benzene will change the temperature this amount. Okay, but I want to know, well, then what is the boiling point? I mean, the freezing point. So it was, the freezing point, if you look on the chart, is 5.49 degrees Celsius. Okay, that's the freezing point of benzene. Okay, but it's going to change by 3.98. Now this is called freezing point depression. Now, depression meaning lower. So you're going to lower the freezing point by 3.98. So you do 5.49 times minus 3.98, which is 1.51 is your new freezing point for benzene. Now, when you're doing boiling point, the only difference is it's the same formula, so I could just put B right there. So now you're going to look at the constant for boiling. So if you look at this chart, you'll use for benzene 2.53, and the boiling point is 80.1. Okay, and it's a boiling point elevation. So once you figure out what that change in temperature is, since it's an elevation, you're going to add that number. So for freezing point, you subtract the number you find, and boiling point, you add that number, because you're making it harder to do something. So freezing point, by lowering it, makes it harder to freeze, and by boiling point, if you make the boiling point higher, it makes it harder to boil. Okay? Okay, so hopefully that'll get you started on doing different types of problems. So remember, there is the Henry's law, that has to do with pressure and solubility. There's Rauolt's rule, that has to do with vapor pressure. And then there's the boiling point elevation and freezing point depression. So those are examples of all of those, and I hope this helps you understand everything a little bit better.